also going to say a few words about formulas. Now, let's come back to, remember, 2 plus 3 is equal to 5. And we mentioned this yesterday, and we call this what? We can decide whether it is true or false, and therefore it is called, Brenda, a statement. All right, let's put down that word again, statement. And then also yesterday, instead of having a number, an expression, 2 plus 3, we introduced the concept of a variable. All right, and now we have a what? We cannot decide whether this is true or false, so Chip calls it a variable statement. There's another word that we gave it, an open sentence. Let me just put down the word sentence this time, all right? It's an open sentence, and we cannot decide whether it is true or false. Is that right? Now, one of the things that we would like to do today is to take sentences such as this and make them into statements, all right? And it sounds almost contradictory because we said that we have to have numbers in there in order to decide whether it is true or false. But with certain key words that we'll look at, all right, I think that you'll see what I mean. For example, let's take, now, if I just took the sentence as given there, x plus 3 is equal to 5, can we decide whether it is true or false? Just as written. Sally?
No.
No. Because, why? It has to have a number in there. It all depends on what number we put in there for x. Is that right? Now let me write a sentence in English such as this. For all real numbers, let me abbreviate numbers, all right? For all real numbers x, comma, x plus 3 is equal to 5. Now let me ask you, is this sentence, can you decide whether it is true or false? Ron?
Well, it really depends because what you put in the syllable depends on
No, it says for all real numbers. And then it is false, right? Can we all decide that this is false? All right? Because this is certainly not true for all real numbers. And then let me just indicate this as false. And what we thought was a sentence, what we started out with as a sentence, according to our definition of whether we can decide whether it's true or false, right? It is now a what? It's now a statement, all right? It's now a statement. Let's try another example. For example, there exists, E-X-I-S-T-S, there exists a real number x such that, all right, x plus 3 is equal to 5. Now, what conclusion can you come to about this one, Kirby? It's true, and because you can decide whether it is true or not, we then would call this a statement, all right? And let's indicate this as true here. Oh, let me make another example, write another example. How about something like this? For every real number x, all right, x times x is equal to x squared. All right, what can we decide about that? Todd?
False.
It's false. All right, for every real number x, x times x is x squared. I thought we said about 4 lessons ago or sometime something about x times x. That's why I selected this example. And Steve says, it's true because, right, that's exactly how we have defined x times x, or rather x squared as being equal to x times x. So I think we'll all agree that that one is true. How about one such as this? For some real number x, okay, now let me decide what I'm going to write here. Oh, let's pick x divided by x is equal to 0. For some real number x, x divided by x is equal to 0. Can you think, see, all I need here is one case, and that will make it true. Can you think of one number which will make this true? Barb? Never mind, she said. She first said the number 0, which is probably not a bad try, but notice you'll have 0 divided by 0. And I think you know that that is what? That is, it's 1? Well, I'm not so sure about that, Chip.
Undefined.
It's undefined. Right, we're going to get into that in more detail later on, but I think right now, I think you know enough to, most of you do certainly, to know that this number is undefined. Yes, sir, Bob?
Statement false because
And therefore the statement is false. Good. Now, notice the key words that I have in here. The word all and every. All right, this is one type of a situation in which we have all cases included. Is that right? And over here, there exists, that's a phrase, and for some, there's another phrase which indicates the existence of something in which we need at least one in order to have that. All right? And these words are what we call quantifiers. Quantifiers. And that's why this word is included in our lesson for today. Quantifiers, all right? Now, let's write down some of these key words over here. We've already seen 2 of them in this column. There's the word all. Let me indicate that. Let me write it down here a little. There's the word all, and another word that we have written here is what? In this column, Ron, is every. E-V-E-R-Y, all right? Are there any other words in the English language that you can think of that would be the same as all or every, Sally? Any, good. Any would be the same, and of course if you have any, you probably also can think of the word what? Something, well, perhaps you wouldn't think of it. How about Mary-Lou? Many, all right. I think, all right, let's put down many, but I think with the word many, I'm not sure that we all agree that many includes all in the English language. So perhaps, let's not put the word many in this column. Well, perhaps one word that you might not think about is each, right? Each and every one of you, right, is an expression that we use, for example, in the English language. Now, all of these words, I think, mean the same kind of thing in that we want to include everything in this. Is that right? And it has some sort of a universal notion to it. And as a matter of fact, that's just what we call it, a universal quantifier, okay? U-N-I-V-E-R-S-A-L, a universal quantifier. Now, these words, there exists, there's a phrase, there exists, all right? And what? For some. And are there any other words that you can think of, or phrases, Sally? For many, all right. I think if we say for some, that would include the case, I'm not sure I know what you mean by for most but not all. Is that what you mean? Okay. Well, let's include that, for most. I think that would be acceptable. Any other phrases here that one might think of? How about, yes? At least one. Very good. At least one. And as a matter of fact, let me put down something like, perhaps you might not think of this, how about there is or there are? All right? There is someone in this room who got up at 7:30 today. Is that right, David? All right? Now, all of these words imply the existence of something, all right, in which we need to have at least one example. And as a matter of fact, there's a fancy word that goes with this kind of a quantifier that we might as well use, and it is called the existential. Wow, can you all say that? Existential. E-X-I-S-T-E-N-T-I-A-L, the existential quantifier. Okay, the existential quantifier. And notice, when you include these words in a sentence, you then can decide whether it is true or false, and that makes it into a statement. All right? Now, let's call all of this our first idea for today. And as a matter of fact, we can use some of these words, some of these quantifiers, to help us with our set notation when we're talking about sets. And let me write an example, and I think you'll see what I mean. Let's start up here. The set of all x such that, all right, such that, now let me make something up, such that x is equal to 2n, comma, where n is a natural number. All right? Here is a sentence that I wrote out in the English language. The set of all x such that x equals 2n where n is a natural number. Now, what I'd like to do is to write this in somewhat of a shorthand notation, all right, with our set notation and what have you. Now, of course, the set of, all right, this phrase, you and I have interpreted by those braces. Is that right? That means the set of. Let me indicate that by rewriting it down here. The set of. I'll just indicate it on this brace, but I think you'll all agree that it also applies to that one. Now, the notation that we use is a set of all x. And the way in which we handle that is to put just the letter x in here, all right? And as soon as I write that x, you and I will interpret this as all x, okay? Now, such that is, there's all x, such that would be abbreviated simply by a colon, all right? Instead of all x, such that, and now I'm going to write something here such that whatever it is that I want to say. And what do I want to say here? Such that what? X equals 2n, all right? Let me put in a comma, or in fact, instead of the comma, let me write the word n, okay? And what do we want to say about n now? What do we want to say about n? Well, the phrase is given up here where n is a natural number. So how may I symbolize that from what we know, Dave?
We'll put n and then put it.
And that little symbol, what do we call that symbol, remember? Is a member of, good, n belongs to
And then a
capital
capital.
N for the set of natural numbers, all right? So this rather long sentence here can be abbreviated to this sentence here, is that right? Okay? That looks pretty easy, doesn't it? And it's quite compact, and you're going to get used to this notation, all right? It's both the notation and the idea behind that notation that I want you to make sure that you understand. All right, let me indicate this by such that, and then whatever follows, all right? And all of this in here is whatever we want to have hold true about x, okay? Now notice, by the way, can anyone think of a set that this is equal to? Let me try to squeeze it right in here. Let's try to list the elements of this set. How can we do that? What does this notation mean? Let's use this notation. Well, it says that n is a natural number. All right, well, what's our first natural number? When we start counting, our first natural number, Steve says, is
1.
1. All right, so let's let n be 1. So therefore, the set of all x's such that x equals 2 times 1 gives us the first value of x to be what? 2. All right. What's the next value of x? Brenda? 4. The next value? Sally? 6. The next value? Jane? 8. The next one? Mary Lou? 10. And about now, we get tired of writing these, and what am I going to do here? Steve?
3 dots.
The 3 dots, 1, 2, 3, and then the end of our set brace. And I think, well, can I put an equal symbol here to say that this set is equal to this set? All right? And as a matter of fact, when you look at that set, what set of numbers have you ended up with? Chuck?
Set of even natural numbers.
Even natural numbers. Is that right? Okay? So, this is a fancy way of describing, notice it's a description or a rule, it's a fancy way of describing the set of even natural numbers. Very good. All right, let's decide to call this our second idea for today, and then look at a third one in which we would like to look at formulas. As a matter of fact, right there, if I look at x equals 2n, all right, notice I have a variable x, right? X is a variable, we'll all agree with that, and n is a variable, so that for the first time in the same equation, we have one variable in terms of another variable, all right? And And this is an example of what we will call a formula, F-O-R-M-U-L-A, all right? In which we'll have one variable in terms of another. Now, let's try to think of some other formulas that you have worked with in the past, and just make up some more examples, all right? Well, let's see. I'll bet if you think back in terms of some of your earlier work in geometry, all right? So a little bit of things that you did with geometry. We call the line passing through the center, this chord which passes through the center taught as the diameter. Let me call that D, all right? And of course, from the center to a point on the circle, you and I have always called that the radius. All right? Now, can anyone give me a formula that relates D and R? Very simple formula that relates D and R, Chip.
D times, R.
Careful. Just the relation. What do you know about? Well, here's R and there is R, so what's your relationship there, Dave?
1/2 D equals R.
All right, or another way of saying the same thing, Brenda, is D equals 2R. All right, let me write that one over here. D is equal to 2R. And if I use the capital letter C to refer to the circumference, I think you learned a formula that had to do with circumference in relation to the radius. Ron? C is equal to pi times D, all right, in which the circumference is equal to pi times D, where of course pi is, by the way, what kind of number is pi? Let's think about our number system, and where is pi in relation to some of the other? Yes, a rational number. What do you think about that? Is pi a rational number? Ron? It's irrational. Oh, that's a big word. And if a number is not rational, all right, there's another word that we use. Well, what are we talking about? What have we been talking about in terms of our number system, Brenda? It's the set of real numbers. So pi is a real number. It's an irrational number, and it's in the set of real numbers. Good. Does anyone happen to remember? Suppose I shaded this region, this circular region here, and I'm interested in the area. A, call it, for this circle, and Chuck says the formula for the area?
Pi times radius squared.
Pi times radius squared, which we may write as pi r squared. Is that right? Okay. This is a formula, because it relates one variable in terms of another. All right? Well, let's look at another example. For example, let me pick out a rectangle. All right, we all know what a rectangle is. Let's decide to call this a length. And let's call this W for the width of the rectangle. And can anyone give me a formula for the, let me write over here, for the area? That is, again, the cross-sectional region. That is the region of this figure that we have here. Someone who hasn't had a chance today. 10. Length times width. The length times the width. Notice in this example, we have one variable in terms of what? In terms of, you see in all of these we had x in terms of n, that's one variable in terms of another. Here's again one variable in terms of another, one variable in terms of another. So the first example here, Brenda says one variable in terms of two others. Very good. Okay? Now, how about if I use the letter P to refer to the perimeter? Remember, perimeter is simply the sum of the measures around the figure. Here we have L plus W plus L plus W, and Todd says
Equals 2L plus 2W.
2L plus 2W. Can anyone give me another way in which I may write that? Ken?
2 times L plus W.
All right, 2, and I think what you meant by that, when you implied by that, was parentheses, one of those grouping symbols of L plus W. Is that right? Okay. All right, let's see what other kinds of geometric figures that you know about, and something that you know about. Let's consider the case of a triangle, all right, in which suppose this is, say, the base B, and let's say that this is the height 8. And what do you know about the area of a triangle? Do you remember any formula for the area of a triangle, Sally? Base times altitude. Well, that's the same formula that we have here. This is base times altitude. And I think if I drew a diagonal of that, what have we done when I draw that dotted line, Sally? You split it in half, all right? So you suspect that the formula for the area of this triangle is going to be 1/2 of the base times the height. Very good. Area is 1/2 of the base times the height. Okay? And of course, if I called this little length A, this side of length A, and this is the length B, and this is the length C, and they're all measured in the same unit, all right? What then can I say about P for the perimeter of this figure, Chuck?
A plus B plus C.
A plus B plus C. There's a case in which I try to dream up 3 variables, one variable in terms of 3 of it, all right? Well, all of these are examples of formulas, all right? Each one of these is an example of a formula, and I think that's about all that we need to do for today, all right? Now, let's turn to our book, and let's look on page 37. I'm going to ask you to do for homework for tomorrow, for the next day, next assignment, 1-25, the odd. Now notice the problems go on up here to 33. But I think in these problems there's quite a lot of computation in some of them, so I'm only going to go down through 25, all right? And also, the next time when you come in, we'll have a quiz. Now the quiz will be on the sections 1-7, 1-8, and 1-9, okay? The last 3 sections, which is since the last quiz. And then, all right, then after that, what we'll do will be the extra for experts in this chapter, and then in fact we'll have a chapter test on chapter 1. Is that clear? Okay? So let me then write down the assignment, and that will be our lesson for